Hi everyone, we're going to start a new topic with this video and the topic is rate of reaction and energy changes. Now this does actually split over paper 1 and paper 2 of the AQA course, but we've put it together because they lead into each other quite nicely. So make sure that you've got your book or a piece of paper, make it clear that we're starting a new topic. This is chemistry, so you might want to write that down as well, and then we'll get on with the rest of the lesson. So the title for today's lesson is actually collision theory. So please pause the video, make sure you've got collision theory and today's date written down. Make sure you've got somewhere relatively quiet to work. You've got a pen, maybe a pencil, and plenty of paper. And to start the lesson, what I'd like you to do in your book, without looking it up, just from your head, I'd like you to draw me 3 diagrams to show how the particles are arranged in a solid, liquid and gas. Now I've got boxes here that I'm going to put the particles in. This is something that's covered at Key Stage 3 and you have gone over it in Year 9 as well, although that's quite a long time ago. But pause the video, draw your 3 diagrams and then I'll go through what the diagrams should look like when you press play. Okay, so the first diagram that we're going to start with is the most simple one, which is the gas diagram. Now in an exam you can get away with just drawing 3 particles spread out in the box as far apart as possible completely randomly, and it will be marked correctly. I've got 4 particles here, but 3 would be fine. The next most simple one that people are okay with drawing normally is the solid, and most people will draw the full box filled top to bottom, which is absolutely fine. I would always recommend not to make your circles too small. I've got the benefit here of copy and paste on PowerPoint, but you can make your circles much bigger. Always a good idea to start from the bottom of the box because solids will sit on the bottom of the surface, they won't float in the air. Now the last diagram is the liquid, and this is the one that people tend to find really difficult. And a lot of people tend to draw something that looks like this for a liquid, which would actually be completely wrong. That is actually a condensed gas. Now some people might have drawn this for a liquid and that would still be marked wrong in an exam. So how do we draw a liquid? Well, the best thing I can suggest is to imagine that the solid diagram that we're looking at here is a box of balls, snooker balls, ping pong balls, marbles, something like that. So I've got a tray here of ping pong balls, and you can see that the ping pong balls fit perfectly in that box, end to end, and they can probably jiggle around a little bit, but they stay in their positions because the box is the perfect size. Now, if you were to take one of those balls out, maybe 2, but even just one ball out of that box of ping pong balls, and then give the box a shake, what would happen to the balls in the box? Well, if you think about it, the balls would have just slightly more space to move, and they'd be able to jiggle around a little bit more, and they'd be able to get out of that arrangement, and they would no longer be in rows and columns. And what we'd have instead is we'd have the diagram that we're looking at here for the liquid. Now you can see that that box is practically filled up and all of those balls are still touching, and that's exactly what particles do in a liquid. All of the particles will touch. If there is space for the particles to move down, then they will. And in actual fact, this particle just here that I'm going to label with X, because there's some space underneath it, really that particle should be dropping down to fill that space. In an exam, you can get away with having only 50% of your particles touching, but it does have to be 50% judged by eye of the particles touching each other for it to be considered a liquid and not a gas. Now we can also simplify the drawings a little bit. As I said, we don't have to draw the particles really small. You can get away for a solid with just drawing 3 rows and 3 columns, so 9 circles would still be a solid. Some exam questions will allow 6, but 9 is your best bet. And as I said before, make sure that it is on the bottom, it's touching the bottom of that box, because solids will sink and they will sit on a surface. The liquid, we don't have to fill that box up, but do start from the bottom, because liquids fill containers and take their shape. And if you pour liquid into a glass, it will go to the bottom of that glass, it won't float to the top. Make sure you've got those corrected diagrams in your book. You don't have to scribble out the incorrect ones. Maybe just write notes as to why yours are wrong. It's all part of the learning process, and you'll remember more if you make mistakes and then correct them than if you just write down the right answers. So once you've got your corrected diagrams, and you can leave them as the full boxes as they are on the screen here, what I'd like you to do is to pause the video and match up the diagrams to the explanations underneath. I would like the explanations written in your notes. You can put them as bullet points instead of the paragraphs, but do make sure they're written down with the correct particle diagram. They're not in the right order at the minute. So pause the video and press play when you're done. So the first one here that you need to be matching up, we've got a solid. So in a solid, the particles are held close together and can only vibrate. The forces between the particles are strong, enabling them to hold their own shape. In a liquid, the particles are held quite tightly together with only small gaps. The particles move around each other to take the shape of their container. Now, when I say they move around each other, the example I tend to use would be if you imagine a very, very busy tube train. You go up to London, it's rush hour, and you're in the middle of that tube train standing up, and there is no space for moving. Everybody is shoulder to shoulder, armpit to armpit, and you need to get off at your stop. Now, the way that you would get off the train is you have to shuffle around people, and you have to move around the people, finding any gap that you can. That's how the particles move in a liquid. They move around each other. They can't move freely wherever they like. They can only move around each other. And then finally we have a gas. There are no forces, practically no forces. It's actually something we look at later on. There are very, very small forces, but we can get away with saying no forces. No forces between particles, and the particles move as far apart as they can. They will spread to fill that container. Make sure that's all written down before you move on. So the next thing we're going to look at is reaction rate. So this whole topic is looking at rate of reaction and then the energy changes of those reactions. It's all tied together. So we're going to start in the next few lessons looking at the factors that affect rates of reaction. And by rate, I mean speed. So we've got a list here of different examples of chemical reactions taking place, even the ones that sound like biology, still involve chemistry. So I'd like you to read through this list and write them in order from slowest to fastest. So we've got strawberries going mouldy. Apologies for the typo there. That's not supposed to be mouldy. So strawberries going mouldy, rusting, the fermenting of sugar, burning fuel, for example, alcohol or a candle, cooking toast, milk turning sour, and an explosion. So pause the video and put those in order. Press play when you're done. So the slowest reaction on that list is actually rusting. So here I have a picture of an old tractor. Rusting is the process of iron reacting with oxygen to make iron oxide. Now, the only thing that is called rust is iron oxide. People tend to assume that any metal that's kind of already brown colour is rust, but iron oxide is rust and nothing else. Now, this process takes quite a long time. It takes many years sometimes. It can be sped up, looking at the conditions. So you tend to find that places that are damp, particularly by the sea where you've got damp, salty air, that will increase the speed of rusting. Now, the reason behind that is all to do with electrochemistry. Something we look at A level, but we don't need to worry about that for now. The next slowest reaction is the strawberries going mouldy. Now, it does depend on the conditions. Some people might argue that some of the other reactions are quicker, but we'll just go with this one today. So the strawberries going mouldy will take a few days, perhaps even a week. It depends if you leave them outside, you leave them in the fridge, but the mould growing is quite a slow process, but not as slow as the rust. So next on the list, I've gone for milk going sour. This is a process where basically the milk is going off. So you can see here that we've got the milk separating, inside the bottle we've got solids and we've got the liquid separating apart. If you put that into your tea, you'd notice that you'd get quite a lumpy cup of tea. And if you look at the bottle is actually almost fit to bursting. So there's gases being produced that are causing that bottle to sort of increase in size and inflate. Next on the list, we've got sugar fermenting, and I've got two examples here. One, a picture of a solution of sugar and yeast in warm water, actually in a lab. And so this is watching the yeast consume or digest the sugar, producing carbon dioxide as a byproduct. And we'd also be having ethanol being produced as well. So this is how we get alcohol in alcoholic drinks. But the exact same chemical reaction takes place when you make bread. And this is bread dough rising in a bowl before it gets cooked, and it's exactly the same chemical reaction, but in bread the dough catches or traps the carbon dioxide gas, and that's what causes the bread to rise. And when you look inside your bread, when you're making a sandwich, the little holes, the little bubbles in the bread are from the carbon dioxide. Next on the list, we've got bread toasting. You can see that that's a quicker process. You can see the toast going brown, so I think that one's quite obvious. This is basically just burning, okay? So you're combusting the bread. That's why it goes black. Next, we have fuel burning. That's a quicker reaction than the toast. Not much to say about that really. I've got an alcohol burner here that like we'd have in the lab. And finally, we have an explosion. Very, very quick reaction. So we can see there we've got a whole host of different speeds of reaction. And this topic is going to be looking at the beginning at how we control those rates of reaction, how we can change the conditions to speed up or slow down the reactions. And we're going to be looking at how we measure the reactions. We're going to be looking at how we can calculate rates of reaction and all sorts of things. So today's lesson, I said, was called collision theory, and we are going to be looking at that now. And as it says on the screen, I don't want you to write this down. So put your pen down, and I just want you to listen to what I'm going to be saying and what's going to be coming up on screen. So just take it in, don't try and scribble it down. In order for particles to react in a chemical reaction, they must collide. Now what I mean by that is that we can't just put A plus B together in a beaker and expect C to form. A and B must collide in order for C to be made. However, not all of those collisions between A and B will result in a reaction. Quite often, the majority of the collisions won't result in C being formed if A and B collide. Each of the collisions must be of a high enough energy in order to overcome each reaction's specific activation energy. Now, I've said here each reaction's specific activation energy. A and B, as chemicals reacting together to make C, will have a different activation energy to C reacting with X to make Y. So all reactions have different activation energies. But all of those collisions, for them to be successful and result in a reaction, must be meeting the activation energy of that reaction. We can control the number of the collisions and how much energy the particles have in order to make sure that more of the collisions result in a reaction. So if we've got our mixture of A and B, we can either change the conditions to make sure that the A and B collide more often, which means that we're more likely to get successful collisions, or we can give A and B more energy, which means that when they do collide, they're more likely to meet the activation energy. As I said, all of this is stuff that we're going to be looking at in the next few lessons. And there are four main ways that rate of reaction can be controlled. These four ways are temperature, concentration, which does actually have the same effect as pressure, surface area, and the addition of a catalyst. Now we're going to be spending a lesson pretty much on each of these as we go through the next few lessons. So we're going to be looking at each of these in detail. There are practicals that go along with this, some of which I might be able to get you having a go at with some kitchen equipment and kitchen ingredients, but also with videos. So have a think about what I've just said. Okay, the next slide is going to be a copy and complete. So I want you to have a go of that. So here's the copy and complete. Okay, read it through. See if you are able to fill in the gaps. Make sure you've got that written in your book. And I am going to say pause the video. But if you get stuck, press play, because you will get some words in a word bank at the bottom of the screen, although some of the words in the word bank are a bit of a red herring. So there are more words in the box than there are in the gaps. But pause the video, have a go, and press play if you get stuck. Okay, let's go through the answers then. So for particles to react, they must collide. That's the most important thing about collision theory. And that word collision and collide needs to be written into your brain. You need to remember that really carefully. These collisions provide the particles with energy to react. This energy is the activation energy, and we write that as capital E subscript little a. Each reaction, has a different activation energy. If the collision is not hard enough, there will not be enough energy to start the reaction. The speed the reaction progresses at is known as the rate of reaction. This can be affected by 4 things: temperature, concentration, surface area, and the addition of a catalyst. Now, as I said before, concentration and pressure, they work in the same way. Concentration is the number of particles in a given volume of solution, and pressure is the number of particles in a given volume of gas. They both affect rate of reaction in the same way, and you tend to find that just concentration is written down, but pressure is there as well. So just have a little bit of a pause and look at the definitions that you need to know. So rate of reaction, we haven't talked about so far, apart from saying that it is how fast a reaction occurs. And we can give us a specific definition that you do need to know. And rate of reaction is defined as the change in concentration in a given amount of time. Now, as I said, that is a definition that you need to learn, so make sure that you have that written down. And we can just have a look at a couple of examples for this. We could be looking at the amount of product produced in a given amount of time. So, for example, collecting gas and looking at how much gas is produced in a certain number of seconds. Or we could look at the amount of reactant used in a given amount of time. So we could be measuring how quickly magnesium ribbon dissolves in acid and looking at how quickly that magnesium ribbon appears to disappear. As I said, pause that, make sure you've got the definition and the examples written down. The second term that we have to look at today is activation energy, and you do need to know the definition of that. And that definition specifically is the minimum energy that particles must have when they collide in order for a reaction to take place. Now we can say for a reaction to be successful as well, or for a collision to be successful. That's something that you can write as well, but the bit in the yellow box is absolutely fine. So I said, pause the video, make sure you've got both definitions in your book. Now we're going to move on to have a look at activation energy in a bit more detail. We're going to have a look at a graph. Slightly silly little model we're going to look at, but hopefully it will help you understand. So we've got a little scenario here where we have this chap called Bob. This is Bob. Now Bob's on his bike and he lives a little bit away from his school, and he lives over a hill from his school. So to get to school in the morning, he's got to ride over this hill to be able to get there. Now, if Bob doesn't eat a decent breakfast, he won't have enough energy to be able to ride his bike over the hill from his house to school. So if we see what happens, he goes up the hill, he can't quite get over the top, and he ends up just back where he started. Now, this is a little bit of a silly thing to be looking at, but we can use this analogy or model to help explain activation energy in the form of a graph. If we relate this to a chemical reaction, Bob's starting point on the left-hand side of the hill would be the reactants of the chemical reaction, and school, where he's trying to end up, are the products of the reaction. And the hill is important to us, and this is the graph that we can look at. Now, if I add here the y-axis being energy, we can see for this graph the reactants are higher in energy than the products. We can get graphs the other way round where the reactants are lower in energy than the products. It doesn't really matter. So the y-axis is energy, and we don't actually need an x-axis. These diagrams can go without one, but people tend to be a bit, they tend to find graphs a bit strange without an x-axis. So we can put one in, and it tends to be labelled reaction progress or progress of reaction. It's not really measured with time, because these are really just sketch graphs when it comes to the x-axis. But what this is showing us is a reaction profile. It's showing us how the energy changes as a reaction progresses. So this term reaction profile is an important term to learn. And as I've already said, it's a basic graph showing the energy changes in a reaction. Now, the end of this topic where we look at energy changes, we'll be looking at these graphs quite a lot. Now, the difference in energy between the energy of the reactants that I've put here in red and the top of the bump that needs to be overcome is equal to the activation energy. So if we were to measure the length of that red arrow that I've just drawn on the y-axis, the activation energy would be equal to the difference between x and y where I've put them on that graph. Now what I need you to do is to make sure that you copy that diagram, labels and everything else. So pause the video, get that in your book, and then press play. So as I've said, we're going to look at these profiles later on in the topic. We'll be looking back to them, but I just want to focus quickly on this one that I drew on the left-hand side just quickly. Sorry, right-hand side, can't tell my lefts and rights at the minute. So activation energy is the difference in energy between the energy level of the reactants and the top of the peak. So for this little activation, this little graph I've drawn on the right-hand side here, the activation energy would be from where I've just drawn that blue line, and it would be from there to the top of that peak. So that would be the activation energy. It always goes from the reactant energy to the top of the bump. So we're going to look now just at controlling rate of reaction and think about why we might want to. Controlling rate of reaction is very, very useful, and it's used in all different places, industries, factories, shops, homes, all over the place. I want you to just have a think and see if you can make a list of particular circumstances where we might want to control or change reaction rate. So pause the video and see if you can make any notes. So why might we want to control rate of reaction? Well, first of all, the main reason that people want to control rate of reaction, particularly in industry, is to make the rate faster to make products more quickly. And the reason that we do that is because that means that you can sell your products more quickly and you make more money. So industry and factories are always trying to find ways of making rate quick, safely and cheaply. We also might want to increase the rate of reaction to get rid of reactants faster. Now, if you've heard of something called a catalytic converter, that is something that is found in the engine of a car that helps to get rid of pollutants and break them down more quickly. So sometimes getting rid of reactants is actually what we want to do. It's not necessarily about making the products. Then we also may want to decrease rate of reaction. We might want to slow a reaction down. Can you think of any circumstances where we might want to do that? Well, we briefly talked about one earlier. We talked about strawberries going mouldy and milk going sour. So we often do want to decrease the rate of reaction to stop things going mouldy, and that's why we use fridges. We are going to be spending a lesson looking at temperature and how it controls rate of reaction, so that's something we are going to talk about in more detail. So, as we've said already, by controlling the collisions in a chemical reaction, we can either speed up or slow down reaction rate. It is all down to controlling the collisions, either the number of collisions or how energetic the collisions are. So just make sure you've got those notes written down, ensure that you're really clear that it's about collisions. And if you've got any questions about anything we've covered in this lesson, please send me a message and let me know.